can start. Okay, good afternoon to everyone. I'm very happy to introduce a very distinguished speaker today. It's Dr. Ben Calloni, who is a Lockheed Martin Fellow for Software Security. He has really a very extensive experience on many different security areas. So we are really lucky that today is with us to share some of his experience.
Alrighty, thank you, Doctor. By way of further, you can see from the screen that I actually represent the corporation on several international consortia, standards bodies, some dealing with system assurance, some with trusted technologies. Used to be heavily involved in real-time embedded systems. This is a research project funded by the Air Force Research Lab and the Department of Defense. I had a co-researcher, Janana Kampara, KDM Analytics, was my subcontractor on this one. A process to look at trying to automate vulnerability assessment, some work we'd previously done, and this is some follow-on work. So this is kind of the overview of what I'm going to talk about today, a little bit more of a philosophical up front, and then a little more technical at the end. And so I work with Joe Jarzenbeck regularly at the Homeland Security Software Assurance forums on pushing software assurance standards and metrics. And right now, the biggest problem we have is if we go into a global economy, we have stuff coming into DoD and government systems from who knows where and who knows what's in it, and mitigating that supply chain risk as we bring those into particularly sensitive and classified environments is, to say the least, causing us some headaches. And I'm hopefully meeting with some faculty tomorrow that can give us some ideas on what we might be able to do. Truth is an interesting concept, and it's transcultural. A truth is true everywhere for everyone. For example, whether I write 2 + 2 = 4 in English or Roman numerals or Hebrew or Greek, whatever the symbology, the bottom line is this many plus this many equals this many. And that's true everywhere for everyone. However, truth will be unchanging, but our belief about things, systems, can change. For example, for many, many centuries, man believed that the earth was flat until Copernicus and others and certain events occurred and we discovered that the earth is round. But you know what? There's still a whole lot of folks out there in the world still think it's flat. If you don't believe me, Google the phrase Flat Earth Society, and there's some very well-educated, good-intentioned people that still believe, contrary to the truth, that the earth is flat. Beliefs cannot change a fact, no matter how sincerely you hold them. That's a true statement. And truth is not affected by the attitude of one sharing it. Just because I'm arrogant and belligerent and declare something to be true does not make it not true because of my attitude. And contrarily, somebody being very humble saying something is false doesn't make it true because they've got a humility about them. So, truths are absolute. Contrary beliefs and opinions are possible. Contrary truths are not. So, in a way of a rhetorical question, George Washington is the first president of the United States. Well, there are some historians that will say it was really a guy named John Hanson who was elected president of the Continental Congress, but that does not mean he was the first elected president of the United States. But what I'm really focusing on is the only things I can know to be true are the things I've experienced firsthand. Would you agree with that? Everything else I've had to read in some book. I've had to determine something. And then I have to make an assessment if that document has some basis of merit to believe that what it's telling me is true, because I never knew George Washington firsthand. The only evidence I have is all the history books and history writing that tells me that, and because of that that evidence, I then make a determination that I choose to believe that is a true statement. And if you think about most of our life is based on that kind of essential understanding. Assurance is just that sort of same thing. I have to believe certain assertions that this system is secure, or at least secure to the point I can trust it to do things, or it's safe, like in an airplane. The assurance processes in our work gives us a foundation for that belief system. They provide the reasoning and the evidentiary artifacts that underpin our belief system, that when I sign off and say this system is secure to some level of trust, that it's done so. Is it absolutely true? No, but to the best of my judgment, I can make that declaration. Nothing is absolutely 100% secure. Nothing is absolutely 100% safe. That's the reality of life we live in. The problem is the more complex the system becomes, the more difficult it gets to construct that belief system and that evidentiary stuff to understand and make the assessment that indeed it is safe or secure. So, what are we left with? Security presents us two different things to human beings: feeling and reality. On the feeling side, we have intuition, emotion, fear, anger, joy, hope. On the reality side, we have our logic, our rationale, our cognition. I have been in meetings where certifiers of multi-level secure systems, multiple certifiers, can look at the same exact evidence, and one of them says, that's good to go, release it, and another says, no, I need you to do a little more work here. Why? Their belief system, their feeling is based on filtering what they see, and I still come back to it's a judgment call when we're all done and through, and that's part of what I'm talking about tonight. Tomorrow night is that whole basis of ethics for how you make that final determination. As it becomes more complex, we do better jobs by working with models mentally to understand the reality, because the reality is so complex, we have to break it up into smaller models to understand that, and that helps us to get our feeling in sync. And you know what? For the most part, human beings over the centuries have figured out how to make those things match fairly well. Surprisingly, our feelings match oftentimes with surprising accuracy the reality. But to get security, to get safety, you got to trade something. Right? You got to look at things. My wife would like us to put in a burglar alarm system, but I've done the risk analysis of where I live and all that, and I've come to the conclusion I'm not ready to trade off the cost to put one in and the monthly fee, because I can pay for something that makes me feel secure and I'm no more secure. Right? Or the contrary. But to get that security, we got to trade off either money or freedom or convenience or something, but there is a trade we must make to get to better security. So, with that as a background, let's start looking at a system assurance problem, because system assurance really deals with something that is a little subjective, and that's trust. So, I have to have a systematic, measurable way to look at a system's ability to execute and prevent malicious attacks. Strong dependency on the supply chain in those systems are necessary. I want to try to eliminate as much as possible unforeseen software bugs. I got to make sure I have the correct safeguards in there, and I need to do this in a cost-effective manner. As an example, I could build a car as safe as an airplane. Are you prepared to spend $250,000 a vehicle to have that? The answer is no. So, we have to be cost effective. Trustworthiness requires us first to understand the threats and what they're going to do. Find the weaknesses that would constitute vulnerabilities, and then make assessments on what we need to do to fix those vulnerabilities. Confidence is really arrived at through an analysis process. We specifically have assurance goals and claims that the weaknesses are identified and mitigated. We perform an assessment to justify that those claims are structured, and then we live with, if you will, the resulting risk of all that. It really boils down to, I make a claim that this thing is secure or safe. What is my evidence to that? And then here are my arguments to connect the two. And again, I can lay those out to 3 different people, and all 3 of them may subjectively say, that looks good, I'm not sure, or no, do some more. That's the subjective part of it, but we can at least get there. And so trustworthiness is, if you will, directly related to the risk and the confidence. The greater confidence I have, the lower risk I have, the more trust I'll put in it. If you swing theta to make it much smaller, I have a whole lot of risk. I can't get a lot of confidence when I have a great deal of risk, and therefore I will have less trust in that system. So, in the threat analysis, what do I start with? Well, what's the CONOPS for the system? How's it going to be employed? Quantify its assets, its safeguards that I'm going to employ. What are the operational threats to the system? What about attack and entry points to that system? All those have to be categorized. I have to think outside the box. I have to think like an attacker to be able to defend against an attacker. And then ultimately, if they break in, what's the injury to the system? That knowledge defines the weaknesses and could constitute the weakest links for the system. In safety security, the two things we always do is we revisit the design, we will always find a weakest link. If that weakest link is unacceptable, you do some re-engineering. Revisit the system again. That weakest link is gone, but guess what pops up? Another weakest link. You do that iterative process till you eventually get to a weak link that you can live with. You can accept the residual risk. Okay, so from the CISSP body of knowledge, a vulnerability is defined as a flaw, the attacker has access to the flaw, and the attacker has an exploit to that flaw. I must have all three to have a vulnerability to a system. A software bug in and of itself does not mean I have a vulnerability. A software flaw or a bug that the attacker can get to, but if he or she has no exploit, it's still not a vulnerability. All must exist. So we don't always have to fix every single bug. I work on some of these boards with the Chief Security Officer of Oracle and Microsoft, and you know why a Patch Tuesday happens at Microsoft? Somebody found a vulnerability, i.e. there's all kinds of flaws in the system they don't fix. It's too expensive. Only when there's an exploit that occurs and an attack vector occurs do they then worry about fixing the vulnerabilities. Otherwise, Microsoft would start costing you $2,000, $3,000, $4,000 a license. You would never buy it. Risks. Risks are the probability then that the vulnerability will be used and that they will actually do it. Now that's interesting. I like to use the analogy that if I'm in a large city in the north and a lot of people don't like to use air conditioning and open windows, if I'm on the ground floor of a tenement in New York City or Chicago, I'm probably not going to open my windows if I'm on the ground floor where anybody walking by, such as drug addicts or others looking for target of opportunities, might crawl through the window. But on the other hand, if I'm on the 40th floor and there's no fire escape near that window and somebody has to deliberately rappel down from the roof to get in, that risk is much less likely, and I may not worry about putting burglar bars in that situation as a risk mitigation. So just because those things exist, risk still is a probability that the attacker will actually use it. Still another thing to consider. And then finally, the exposure. So what if they get in? What are they really going to find? If it's not of anything of value, probably don't care that much. So, confidence is done through an analysis of assurance and reducing that uncertainty, that feeling that everything is okay. And it does not necessarily provide additional security or safeguards. Let me say that again. Assurance is about trusting what you have enforces the policy of security you've put in place. High assurance does not mean it's more secure. It means I have greater trust that what it is doing to a high degree of defense. Right? It could still be very insecure, but those are two separate issues. Part of that is the assurance case, and what feeds into that is verification. The engineering process has to be known, the authentication, the implementation, and many other factors feed into that. Okay, confidence is a product then of those system assurance activities, those artifacts, those information, those data that we scan over and form an opinion on. We look for those. If I have a lot of evidence that's very highly reliable, and I have claims of that, then I can say I have a great deal of confidence. But on the other hand, in this slide, if I have very high claims but no evidence to support those claims are valid, I got very little confidence that the system will perform as it should. Risk calculation. What's the likelihood that something will occur? If it's extremely high, no matter how much the impact, how low the impact, it's going to be a problem. If the window's open and I'm pretty sure the guy's coming through, I better just accept the fact, no matter what I do, if I leave that window open, I'm going to lose something. Follow? So, how do we systematically start measuring this? And then finally, trustworthiness can also be mapped in terms of if I have an extremely high risk, no matter how great my confidence, I'm in trouble. I've got to reduce risk and have high confidence to be able to have high trust in a system. Okay, so that's kind of the background. And the challenges that we had to look at in this research project was to find a systematic way to cover the weakness space that's out there in our software systems, to find a cost-effective assurance process that could help establish that chain of trust, And current processes unfortunately resist automation. There is not a lot of traceability and transparency in many of the systems we buy. I've been in government workshops that are talking about, and one of them at the Open Group that has great backing from the DoD, NIST, and NSA is something called the Trusted Technology Forum, as a way that from these global suppliers we have some insights into the things they do. To the point that eventually when we get that, the government will say, I don't care who you are and how great you think your product is, if you can't give us some assurance that this thing is trusted, we're not buying it in quantities of 100 and 200,000. So fix it or don't make the sale. So, how do we do that? Right now it's an ad hoc way of doing this, and some of the things we need to do is get more formal methods, more mathematical approaches. We find that this space to do assurance is so large that there's no one vendor, no one contractor can supply it. It's going to require an ability for multiple tools by multiple talented people that are very good at their specific thing at being able to have interoperability to exchange information between the tool sets to establish an assurance case for some of these systems. That means we have to have standards for interoperability between the tools. Hence you see my involvement in many of the standards organizations. Security assurance tools are fairly young, and there's still lots of opportunity. I was talking to the faculty before, and I'm talking to faculty tomorrow. My hope is that in the future I can be interacting with some of the grad students to maybe be a mentor to tackle some of these problems in this space, because it would have direct applicability. Instead of just you write a thesis or a dissertation and you got it and you get your degree and go on, you may have actual impact in DoD to make things a lot better. So, we had a problem put to us by DoD, was the fact that the current static analysis tools, Coverity, Ounce, LDRA, name a dozen of them out there, all good companies, no, I'm not trying to blast them, but they've been built as stovepipes. They can't exchange data with each other. They can't exchange data with other tool sets that could do analysis, such as risk analysis. It's just all stovepipe, which means a lot of manual labor to try to go over tons of data and spot things that you hope you'll find as a human. There's no significant overlap. NSA evaluation showed that of the 5 top leading static code analysis tools, none of them found all the faults in a particular software code I'll talk about later. The integration of multiple tools can be extremely costly. Lockheed, as rich as we are, multi-billion-dollar company, cannot afford to buy 20 different static analysis tools and run all of those against our code. The costs are enormous to purchase, and then to have the labor spent to do that, we cannot do that. We've got to unify a lot of that. And penetration tools, as good as they are often woefully inadequate in many cases, and it still requires a very intense individual to think outside the box to figure out how to break into a system. The tools help, but they are not fully automated. So, many of the tools suffer from a lot of false positives. If a tool half the time is giving me potential bugs that are bogus, after a while I'm not going to rely on the tool, right? Not to say, well, what's it not telling me might be there that it's not even looking for? Those are problems. So it's a shortcoming. This was the basis for our research grant. Within that whole transparency of analysis, we're not looking at the whole supply chain, and part of the problem comes from not just the applications, but in all the calls. What happens to the vulnerabilities between not only stuff within the app that could be a problem, but it's making system calls, and it's the combination or composition. On their own, nothing, but together they can form a vulnerability problem. All static analysis tools only check the app at the source code level and do nothing about the calls into the system and how secure they may be. So, same thing with the programming languages. Example, I got control flows from A to B in the different tasks. I've got to go through the computer components. I've got all additional tasks 1 and 2. It goes on and on with any general purpose operating system, the terminals, the flow of data, the subroutine calls. That's a lot of checking and a lot of stuff to do, and right now I know of no tool that can do that to any degree. But is it possible through some standards and some interoperability, individual pieces of, or individual companies or people could fine-tune a piece of that, and we aggregate those things to where eventually we can build up a suite of things that could work. Okay, so as we worked on this over the several years, we came up with a solution that is a piecemeal but a standards-based approach called the Software Assurance Ecosystem, endorsed by both NSA, NIST, and Homeland Security. It works through ISO and OMG standards, which are all open, and started with a handful of particular rules to put together a more formidable, or if you will, formal way of doing these kinds of analysis. The SBVR, KDM, augmentation meta model, software assurance evidentiary model, and metrics meta model. I'm not going to go into those. If you want to go omg.org, you can download the specs and read them yourself, but they're all designed to work together. The interesting thing about SBVR was that it's a semantic way of accuracy instead of sort of a human way of doing things that have, well, what did you really mean? Designed for business rules. We found that actually can be used in this domain very well. This is what the ecosystem looks like. When I do an assurance in a Lockheed Martin, a Boeing, a Raytheon, people and processes are much a part of that. I have to vet the people and know what their clearances are for many of these systems. I have to know the entire process. What's your trusted process? What's your engineering process? What are your language constructs? What are your modeling tools are you using? What about the system itself? What are your configuration items? How are you configuring those particular operating systems and so forth? All that information feeds into that. And right now it's done through Excel, PowerPoint, and Microsoft Word. And the documentation can fill a room. Right? There is a better way to automate that. Because eventually I want to get this electronically done, that all this feeds into it, that I can eventually get to a repository of all the pieces of information, then the certifier can start making queries electronically. Well, I want to see about how this worked or how that does. Let me see that policy and the traceability to this particular function in this particular processing unit. And put that together. And that's a large problem. That's why we came to the conclusion this cannot be a one-size-fits-all specification, but a roadmap that allows us over the next 5 to 10 years to allow for commercial industry to do what it does best and meet a need in a way that large companies like Lockheed and IBM can buy a suite of things that work together to give us solutions that will work. Hence the feed into open standards. This is just another view of that. I won't belabor the time with that. So, we started with one small piece of this assurance, the fact that all the weaknesses out there now by the static code analysis vendors are all over the place. The work has been funded by Homeland Security, NIST, NSA, MITRE, and DOD, or Office of Secretary of Defense. Much of them were done through small business. Some of them were major contracts like the one I had. We started with, okay, there's all these things called CWEs out there. What's the number one still, top 10 security flaw that is implemented today that represents an attack vector? Do you know what it is? Buffer overflow. Do you know how long in this country and around the world we've been talking about buffer overflows? 15 years or more, and it still happens. Something is drastically wrong. The work was funded by the individuals you see here, Mr. Mitch Komaroff, Mr. John Luke. The name of the contract was the Embedded Information Systems Technology Support, and the actual project was VPAD. We were the prime. KD Analytics out of Ottawa, Canada was the sub. Here's the study that triggered this, that got us this contract. This was briefed at that software assurance forum that Mr. Joe Jarzenbeck chairs out of DHS in 2006. NSA InfoSec evaluators thought, let's see what the state of the art is of all these static code analysis tools. They wrote a who's who of every bug you could put into a C++ programming package. Buffer overflows, all of the wrong things you should do went into it, and they had a team of it go over it and said this represents a very major set of that. Then they got these SEA tools and ran it against this code to see how well they did. They reported this in 2006. Now, perfection does not exist anywhere in the world, whether you call it heaven, nirvana, or whatever. That top right point of all false negatives and all true positives does not exist. But we can get pretty good if we say that thing in the top quartile there to the right is green. If it can do that, report all true positives or mostly all true positives and very few false negatives, that would be a good tool, hence green. You come down a little bit, okay, it's not quite as good in either of those. That's yellow, we'll color code it. And then anything below that, halfway, that tool is useless to us. That's how they started. They ran all kinds of tests, and this was kind of just the top ones that they reported. I've got the actual report. It's for official use only. But, so what they did here is you look at the far right dots, whatever the top color value is of any of the 5 tool vendors, they didn't publicly say which ones they are. I know which ones they are. They are ones you would know. you got the top level. So notice the buffer overflow. One tool did it what they called good or green. One tool did a so-so job, yellow, and 3 of them did a very lousy job looking for what? Buffer overflows, which have been out there. These are the top leading SCA tools. The white means they didn't even bother to check for this particular thing, such as a command injection, which is also a very lethal thing to allow it to happen. Null pointer dereference. I was teaching these kind of things when I was teaching at Texas Tech University in C program about you got to do something with those null pointers and dereference them properly. One tool doesn't look, 4 of them did a very lousy job of checking for it. This is even more telling. In other words, if you take all 5 tools, 84% of the bugs in there were found by one tool only. When you say, well, what about all the bugs that two tools find? I got up at 5 this morning, I'm sorry. Look how small it gets. 3, 4. In other words, it's a hit or miss as to which one you buy and run. But what's even more startling is think about it. If I bought all 5 tools at Lockheed Martin and ran them against my code bases, 16% of the flaws would never be found. For me to reduce labor costs for your tax dollars in my system, I've got to be able to have a tool that I can rely on, because if it doesn't, I've got to put 2-man code teams to review every line of millions and millions of code to find them, because I can't trust the tools to do it. This is a huge cost savings. They repeated the study in 2008 with the same results. NIST repeated a study in 2009 with the same results. The static code vendors were there at these conference meetings and nothing improved. Hence our research. So, we had actually formalized 18 of the CWEs early, in an earlier phase of the project, 3 years ago. And we put them through an SBVR formalization, which I'll describe shortly. We did 18 CWEs. We demonstrated parameterized depth and breadth. We eventually figured out, a lot of these things are similar. I mean, think about it. An out-of-array index, or an index out of array on an array, a buffer and a heap overflow are all things of memory mismatch. I mean, they may have their own names, but they're similar kinds of memory handling errors. So we said, maybe there's something here called a patterning, software fault pattern, that could be unified to use it and parameterize that to look for these flaws instead of this kind of hodgepodge of flat 1,000 flaws. Brings, if you will, order to chaos. We actually created a test generator that we could generate test cases out of C++ or Java. The original one we were able to generate automatically out of the formalized statements of the common weaknesses. 413 cases. We just finished the contract, and matter of fact, it ends in 2 more days, and I got my final report in. We're actually now generating 3.5 million test cases for the flaws. Because think about it, there are lots of ways to do a bug. Out of a formalized definition, you then can systematically generate every possible way to do a buffer overflow, use that as a pattern match then against your code, and come to a better understanding of it, and of finding it. So, what is an SBVR? Well, this is the CWE 78, a command injection. Plain English. These are reported by people that find them to MITRE for this purpose. You can go to the CWE, Google it. You can find all these things in their definitions. And this is what it is, and I won't read it, but it's plain English. The original description is what it is, and the number is there as well. But to do automation, you have to have a consistent vocabulary. I was joking with a class I was teaching at Lockheed yesterday when I went out and found a machine dispenser where I was teaching in one of the buildings, and they had Earl Grey tea. I was thinking, all of a sudden I flashed back to Jean-Luc Picard. Remember he'd say the computer, tea, Earl Grey, hot. But what does hot mean? Right? We're very subjective in our language, and to do automation, you have to have something much more consistent and formalized to automate any process. You've got to identify terms and facts and rationale and structure. Those definitions in our English language don't work real well to do automation. Think about any language you program in. There's something called a syntax. You violate the syntax, the compiler doesn't know what you're trying to tell it to do. Agreed? Same thing here. So when you start going through this formalization contractually, what do you look at? We start looking at these terms. Well, we have something called a software system, an attacker, a privilege, a command input, so forth. Start identifying these in a more formal way. What are facts? Well, an attacker has privilege. An executing process has privilege. Defining this like you would in a syntactical tree to put full definitions to the, and then finally, okay, what's the rationalization? What accepts input? An attacker, who else can provide input, and so forth. And you finally then come up where that CWE 78 gets rewritten into a very formalized definition. Everything underlined, if you think of like a Bacchus-Naur tree on a syntax tree, eventually has to get to a leaf node where every one of those terms is clearly defined. Once I have that, then I can systematically go through that definition and start generating vectors for testing. Until I do that, not going to happen. We originally posed doing this, and there were 632 CWEs that we could formalize at a cost of $25,000 per. That's a lot of money just to get to the formalizations, much less build a test code generator and a vulnerability analysis machine and all that. So our customers said, look, why don't we start looking at these things in a more logical way? What if we go with, instead of CWEs, we start with the idea, like I said earlier, a generalized software fault pattern to look at families of similar things and then figure out how to parameterize that way with fully discernible code artifacts and variants and so forth. So in phase one, we looked at those, and in phase two, we looked at the parameterization. This is some of the CWEs, by their number, that deal with constraint operations within the bounds of a memory location. 3 of those jump out all right well. Buffer overflow, unchecked array index like I mentioned earlier, and stack overflow or heap overflow. Those are all very similar things, but all the things on this page are memory mismanagement. So we looked at what does that mean, how could we parameterize that, and so we came up with this concept that the CWEs could become SFPs in classes. We could formalize those if we could subset them on a much more inexpensive basis, because we would reduce it from 632 to something far less than that, and then put together the patterns and parameters. Okay, it's a memory mismanagement. What are the unique things that make it a heap overflow versus a buffer versus an index, and parameterize those definitions to start doing the generation. So, for example, this is SFP number 8, a buffer overflow. I won't go through it now. The slides will be available later for you, but basically this is kind of what we were looking at in terms of getting to that kind of a definition. How did we do this? We started with the CWE. The hands in the photo are actually the CEO, Janana Kampara, of my subcontractor. They took the picture. They printed out all the CWEs. They had a big table in a conference room, and they started then laying them out all over the place and figured out, all right, we got all this stuff out there, and now what do we do with these 630? Well, they started then looking at this and said, well, these things start to look similar, such as authenticate and actor, and we'll group those together because they're similar types of things. What about some of these things like buffer and heap and all that? So we found that there was a logical partitioning that was occurring as we were moving these pieces of paper around on the table. And we eventually found all of them, and they've lined up in some very nice, neat piles with similar clusters. We then got rid of CWE. No more. We now look at what these are and put them into software fault pattern definitions and parameterize them. Forget the CWE definitions. Let's move to something more structured. This is the full graphical map of all those. Some are major, some are minor. We found out in the CWEs that are testable that there are 310 discernible, 322 non-discernible. In that last graph, there's 21 primary clusters covering them all. And we found out that there were 36 unique fault patterns. This slide set was released last fall. The final report, we did some more massaging, and it's now down to 32. That's the final number, not 36. We can cover the CWEs in 36 patterns with parameters. That's doable. That's cost effective. What is a non-discernible CWE? Well, the problem is, look at number 684. Failure to provide specified functionality. I'm going to need my glasses to see this one. The code does not function according to its published specification. Wait a minute. What do static code analysis tools do? They only have the source code to work on. Unless you got some automated way to get back to see if it matches the design and requirement spec, how do you know that? Well, a human determined that, but you can't automate that. If you'll mentally go back to that software ecosystem picture, remember when I said there's processes and people and design artifacts? As we populate that with standards and tool vendors come forward, we envision at a time there will be a way, as you use things like unified modeling language, TOGAF, DODAF models with full interchangeability, to be able to then say, oh, we can make this one discernible. Because now we can see the traceability from the code to see if it really matches the original spec. What would that do to the quality of software in our systems? So that's why we said an ecosystem that's a suite, not a one-size-fits-all, try to do a big bang. So we had that. We found a way to do that through an automation. We can support it. We've demonstrated that. The computation is defined by the artifacts. One of the key things that helped us was the development of the KDM meta model, which has existed in tool support for years. It's actually an ISO standard. After we got it done at OMG, we were able to get it through ISO. It is a knowledge discovery. It was designed to capture any and all information about a computer system, including configuration items, in a meta model form that you could literally put all the information you need. Let me give you the background on this tool and standard. Nortel, Canada, years ago, had so much deployed, so many switches and hubs and various things they do in telecom, that they had lost track of design and requirements documents for everything they were selling. They had some routers that were being deployed with version 5 software, and when they looked in their archives, the last time they had any update to requirements and design documents were version 2. People had just been slamming code. Management says, we got to find a way to automate this and reverse engineer and get everything up to date. And what they put together was a way that became such that it eventually became what was known as a knowledge discovery meta model. We can do reverse engineering out of binary code. We can take source code. The model tool can be fed into it, and you can start making order of it. And it then becomes a database to query about the system and learn about the system and put things into it. And part of that would be then the SFPs and the weakness space. So in phase 2, we did convert the SFPs to the SBRVR rule set, like I've talked about. We did write a software meta model. We continue to work on the test code generator. As I said, originally we thought it'd be 500,000. We're now generating 3.5 million faulty patterns from these SFPs. And we are poised to continue R&D for data flow analysis. If we can get, and when we get this thing finalized, as we get further into the research, a data flow analysis tool will help us find the vulnerabilities. Right? Once we know what the flaws are, remember that graph where you're just doing the apps, but then you got all these system calls? A data flow analysis engine lets you start with that and then start poking through the whole structure to look for the vulnerabilities, right, to see if they really exist. Because just finding the flaws, like I said, is not sufficient, because it's a flaw plus access to the flaw plus an exploit. Vulnerability requires doing all those, and that requires a data flow analysis, but until you know how to categorize the flaws properly, there's no way to do the other two and look for that. So that's to be discovered, that's to be determined yet. So we came up with, the customer originally wanted a tool for the U.S. government to test all this software that they buy from all over the world before they put it into their systems, a government-only tool. So we came up with the idea, we said the SFP meta model. We said, wait a minute, let's go to the OMG and make this a meta model. Let's not do this as a DoD-only thing, right? This is a problem for all of enterprise America and everywhere else. Bad software is killing a lot of folks. The losses in identity theft are in the trillions of dollars worldwide every year. Those kind of things would be useful outside of just the DoD, so everybody could benefit. But that was their thing. So we said, look, once we standardize these meta models in the SFP format through an open consortia, we can then generate the standardized code snippets in Java, C, C++, Ada if you want to, or any other language that may come along, because it's done in a semantic vocabulary, not a specific language construct, and you just generate the code from the formalized definitions, right? Oops, hit the wrong key. There we go. That would then feed into the U.S. government product acquisition to run against it. There's something known as the Open Group Certification. If you know anything about Unix, you know there's a standardized Unix and a test suite that you get branded that says your API. So if I have an application written on HP's Unix, I can drop it onto IBM's Unix and it will run. That's due to the fact that not the compilers, but the Unix variants are all tested for full conformance to the Unix specification. What if we do the same thing here? Well, once we have that, we can go to Coverity, Announce, Fortify. Guys, we've got a very formal way for you to do this. Here's the way it's going to go. For those of you willing to put your tool, here's the test suites, modify your tool. By the way, we got all this formal stuff here you can use as well, but so that at least your tool will find everything we've agreed are the bad things to find in these standardized code snippets, and make sure you find it. And if you do that, like with the Unix testing, you get to put the brand, the good housekeeping seal of approval, so to speak. Now, that we should not have to distinguish buying a tool because it does a better job than somebody else when it comes to flaws. It should be ease of use, the graphical user interface, cost price break, those kinds of things should be how a discriminator. Not the fact I find a buffer overflow and you don't. That is not good business. And then the government can get into this and say, oh, okay, I see, instead of me having a U.S. government tool only, I license the tools as validated, just like anybody else, a Lockheed, an IBM, or whoever, and we get out of this government-owned only kind of a thing, make it truly a commercial enterprise. Well, companies like Lockheed can then pull in things like this to feed into our DICAP CNA effort. Granted, there's a whole lot there based on that ecosystem. I mean, all the stuff you saw there, we have to give all those documents to our customer, but SCA evidence would be one. But more importantly, when I get to the point, and I'm working on this on an IRAD this year, if I can get to the point where I know that I can trust the tool to do these things, I can then go back into management, to the engineering core processes and say, guys, if we run the tool, we only have to focus our eyes on our two-man reviews on this. At the labor rates we charge per hour, that is a huge manpower cost savings if we can automate it, and our customers would muchly appreciate it. What about an application product? What if you had some kind of a spreadsheet or some other app, any kind of a commercial app you wanted to sell? Now you run one of these validated SCA tools against your tool. Guess what you could do? License the open group, pay them, hey, double check our research, we say that we don't have any bugs in our software based on this standardized set of things. They get to then put the certification, the branding on there. So when I go into Best Buy, oh, here's two products. One says they've run through this and they're free of all these bugs that everybody agrees are things that shouldn't be there, and here's one that doesn't have the brand. Which one are you going to pay the money for? Right? And then finally you can feed into common criteria and several other things. And as we complete the semantic part, hence I said we have an SFP meta model in work, but when we finally get the SBVRs done, much more formally done, then we replace that in the standard, round trip it through the standards, round trip it to the tool vendors, and so forth. Now, what does that mean long term? Well, instead of CWEs, if we find new things, we put it through a process to formalize it, add it to the database, let it know to the vendors, okay, there's a Rev 3.1 of this spec, there's some new things you need to patch, fix, update, and sell it in your next version of your tool. Bring chaos, or bring order to chaos, not the other way around. So we look at this as being an open, fully transparent, fully configurable approach compared to what we have now, which is semi-transparent, if at all, very closed and all that. We see this as a better way to go. The customer agrees. The one thing I appreciate about the customer, he said, look, this really does need to be open standards. This is a problem that we're going to have to solve globally through collaboration in an open standards format. And so that's the reason we're doing it, and I continue to chair some of these committees, because Lockheed wants to be a part of that. Where do we go? Well, we expanded the rule-based analysis from simple patterns and values. The goal is to make the rules available as third party. I'm going to be in D.C. in March. I'm setting up a meeting with Coverity to see if they'd be willing to partner, to be one of the first to try to go down this path. I found out something in commercial technologies. It's taken 10 years to figure it out. All I need is one to do it a better way. Guess how long before their competitors will figure out they got to play the same game or go out of business? That's the wonderful thing about free enterprise. He who builds a better mousetrap will gain market share. And if you want to play, you've got to bootstrap yourself to do a better job. I don't have to convince all of them. I just got to convince one there's a better way, and they can demonstrate it and start making better sales and inroads. We eventually want to get to the DFA. Like I said, that's part of the future research we've got to do, because that will get us to the vulnerabilities. But like I said, until we get some order to the static code problem, the rest is kind of useless. This is kind of an idea where we're heading with the test code generator, the code complexity rules, and then eventually feeding into the DFA engine. It's fairly self-explanatory. I've verbally explained it already. But eventually with the DFA, then we can get out vulnerability reports. We know there's flaws. We can fix those. But what about the vulnerabilities in the interactions? So, in summary, we normalize the uniform common fact model. We want to have that. Standards data feeds for reasoning, standards-based. We want to get the assurance case to a more formal mechanism. The English language is horrible at accuracies. It really is. Think of how many conversations you had to kind of work through when you said something and somebody misunderstood you. Our language is wonderful, but it also, unnatural, is extremely tough to sometimes communicate in, and our computer systems need to be able to do substantive reasoning. SBVR helps us with that. What we're also looking for is full traceability. I've actually done some experiments where I can reverse engineer binary code and feed it through these things and do testing. Because sometimes that's all I get. All I need is a license and approval from the vendor that I'm allowed to do this when I want to check their software. If they say no, then what are you trying to hide? Maybe I don't want to go through with a sale, right? Or better yet, run it yourself, give me the results, and get an independent third party to verify you've done it. Architecture, concept, model, the arguments, policy, and ultimately it traces to the policy. The key value is an end-to-end traceability. That is really what safety and security is about. You strip all the other stuff away. I've got to be able to show that from this requirement, all the way down through all the design, the implementation, the test, all that every line of code in there is there to meet either a safety critical or a security relevant requirement. If I can prove that traceability, I'll get certified to run every time with my DoD customer. I couldn't help but do this, and I've done this before for SPAF. I've known SPAF for years. But I've always found this interesting because when he and I have had discussions before, when I've spoken at the CERIAS conference a few years ago and on a couple of occasions since, he and I are in violent agreement because this is really what the problem is. We don't have a network security problem. We have an application. We have an endpoint solution. The networks themselves are usually fairly secure. It's all the stuff going on at the endpoints where all the stuff shows up. On the individual computing nodes, particular applications, it really is that, and until we start tackling that problem, we're not going to get any better at this. So that's my contact information. I've got about 4 minutes left for questioning.
Okay, so if there are no questions, I'll ask a question.
Okay.
First of all, thank you for this very nice talk.
You're welcome.
So I have a question.
Yes.
So in slide 47, you really show this picture where you have the tools which are certified because they will be able to find all those vulnerabilities. But at the end, those tools will be kind of huge piece of software. Don't we have a supply chain problem for the tools themselves?
We do. And
what if the tool may have a malicious code inside? No, when you test, it works perfectly. Then when you deploy on the field,
that is true. And one of the ways that could be handled, for me to build a multi-level secure system from the ground up is extremely expensive. I can do it, but it's expensive. Some of these key things, maybe that is the solution. We very specifically put the platinum plate, if you will, put the effort in to make sure that we build it correctly from the ground up. And then say, okay, we've done our proof on this particular tool or these particular tools we trust, and then deploy those for people to use them, is an approach. But you're absolutely right.
Yeah.
I've always thought of it now, the way I think of it is the old Turing problem, right? You do the Turing machine, and you feed the Turing machine into itself. It's the same kind of thing. Because I asked my supplier, so did you run the tool against your own tool?
Yeah, exactly.
And they said, yes, we did. And we removed everything that we found.
But then, how do you trust that them tell you the truth?
It is. It's a recursive problem. It really is.
I know, but this will really make perhaps a false security sense into people. Probably those tools may need to be deployed with really kind of attestation techniques, so you can make sure the software, the tool itself doesn't change.
It is. There's a lot that has to be done. Innovation is based on the idea that an individual can build a better mousetrap and sell it and make it profitable for him or her. But innovation in of itself can also be a trap, because to do that innovation, we have to take risks, we have to deploy things, we have to take chances, and there may be problems with that, and that's a balancing act. That really is. I don't claim to know all that get there. I just know that when we saw the problem with the CWEs and our customers saw it and said, we can do a better job of this more formally, at least bring some better way to do it. Not perfect, but better. It's not that I go from something that's untrusted to absolutely near perfection. It's if I can raise the threshold, right, a little bit, and do that globally to every computer, and then gradually increment that eventually we can get to the point where we're doing a much better job. But there is no magic bullet here. There's no, it's just good diligence by researchers and people trying to do the right thing and incrementally taking the next logical step to improve it. And I think the piece that fortunately these customers understand, we're not going to do it in DoD like we used to. We've got to have the partnership of the enterprise and the commercial world and working through the standards and say, guys, this is a better way to do it. What do you think? And have them involved in that process makes that financially possible and still for people to make profit. So,
Yeah, so questions?
yes, yes.
This one.
Thank you. So it looks like in the process of converting your CWEs to the SBVR language, or at least the vocabulary that you needed, you could have benefited from a lot of natural language processing that was pretty semantically informed. Were you able to find and use some tools or some experts from
We
that
did
field?
and we have, and I'm gonna, and one of the things I'm gonna throw out since you're here, and I've been talking about it with the faculty briefly, like I said, there's some key pieces of this that I think would make one very good either master's thesis or doctoral dissertation. And I would be more than happy to work, some of my time via telecom or whatever with your advisors if you want to, because this is all open standards. It's not like it's classified, right? It could be something that there's some pieces we could carve out of this to do that. We did some of that, and the truth is because of cost and schedule, remember I said we did originally 18 CWEs? We were not able to do the complete notice in the thing, we have not completed all the SBVR. That's a lot of work yet to do. There's a lot of formalization that has to occur in there. For us to do it, for my supplier to do it, we're in business to make money. You're in business to get a degree. No offense, your labor is a lot expensive, but your payoff is I get a master's thesis or a dissertation, and I see some key pieces here that might be rolled into that would help not only you, but feed into what we're trying to do. And it's a win-win for both of us, because right now we still have not got full funding to get all those formalized into an SBVR. And there's some work, I think, like you said, that could make that better, and it might be you could write up a thesis or a dissertation and get credit and graduate. So certainly you have the faculty, they know how to get a hold of me, you got my information, and be happy to discuss some of that with you. I'm an adjunct professor, as you can see, at Southern Methodist. I teach system security engineering usually once a semester, so I think my credentials would be acceptable here at Purdue to help mentor some.
Okay, so thank you very much.
Thank you.